Today's numerical session is to find magnetic field intensity at a point due to a current circuit by applying Biot-Savart Law. So the current circuit is as shown in the figure. So it is having a 20 meter length rectangular conductor joined with a semicircle of radius 5 meter and the width, okay, this 20 meter segment conductor is separated by 10 meter. In the sense, I have 1, 2, 3, 4 conductors, okay, 4 conductors connected as a loop. So 1, okay, 2, 3 and 4. 4 conductors connected to form a loop. So now let us see how to solve this current circuit, or how to find what is magnetic field intensity at point B. For this, basically what we are going to do is we are going to divide this current circuit, okay, into different segments. So it is necessary to understand ourselves how this circuit can be divided into different segments and how can we find magnetic field intensity at a point B due to each segments, and then add them to find the total magnetic field intensity. Okay. Now let us choose section 1 like this. So the portion AB, okay, so section 1 is portion AB. So I am going to find magnetic field intensity at P due to this section. So here I will be using the idea of magnetic field intensity at a point due to a finite length conductor. So the magnetic field intensity, okay, for such a case is given by I, okay, divided by 4 pi r sin alpha 2 minus sin alpha 1 in some direction. Now this I is the current flowing through the segment, line segment 4 pi r, in that r is the distance between the conductor and the point, and alpha 2 and alpha 1 are the angle suspended by the line joining two ends of the conductors, okay, that is alpha 1 and alpha 2. So in the figure, refer the figure, in the figure it is marked properly that alpha 1, okay, is the bottom end angle subtended by the bottom end, and alpha 2 is the angle subtended by top end. Okay, regarding the angle alpha 1 and alpha 2, if you have any doubt, you please watch my previous video. So there I have solved a similar current circuit using Biot-Savart Law. So there I have explained this alpha 1, alpha 2 and how alpha 1 and alpha 2 is measured, and why, what are the sign conventions used. Okay, so those things will be skipped in this video. Explanation of those things will not be done in this video. Okay, for that you have to watch my previous video solving similar problem. Okay, now see here, if you consider the triangle, okay, of subtended for alpha 2, okay, or if you want you can name this triangle for reference. You can write this as some point M, okay, so PM. So you have triangle, okay, BPM, and you have triangle APM with reference to alpha 1 and alpha 2. Now alpha 2 is, okay, considering tan, okay, tan alpha 2. Tan alpha 2 is opposite side by adjacent side. So this will be 5 divided by r. R will be say 20 meter. Okay, from the side of the figure, r will be 20 meter. So I get alpha 2 as 14 degree. And by symmetry, alpha 1 and alpha 2 will be same. And since alpha 1 by sign convention, alpha 1 is negative, so alpha 1 becomes minus 14. So now I know the values of I, R, alpha 2, alpha 1. So you please substitute in the equation for magnetic field intensity due to a finite conductor. Okay, then you get the solution as 0.0193 an cap ampere per meter. Okay, so that is the magnetic field intensity at point P due to first section. Now section 2. So what lies where the importance of this problem lies is identifying the sections and relating into point P. If you can do that properly, then every problem is similar. Okay, so I am doing more problems on this because this is a familiar. Okay, these kind of circuit are familiar, popular. Okay, those are attending engineering exams. Okay, this kind of circuitry questions are familiar. Okay, but still there are confusions or there are non-explanations, okay, in most of the textbooks. So that's why I'm doing the video on this. Okay, so those who listen to my previous video, this will be a little repetitive. Okay, but still, okay, average learners can use this video, okay, to practice more problems. So now we have to choose section 2. So I take BC as section 2. Okay, so I finished the left hand side conductor AB. Now refer the original figure. Now I have the section BC. So BC subtend only one angle, okay, with point P. So let me choose that angle as alpha 1. So again I'll find alpha 1 using the triangle. I get it as 75.96. Okay, now going by the sign convention, I have to use alpha 1 as minus. So it becomes minus 75.96. Okay, substituting. Now here you see alpha 2 is not there. Okay, alpha 2 is not there basically, or alpha 2 I can take it as 0 basically, because it's not subtending any angle with the second end of the conductor. So alpha 2 is taken as 0. So when I substitute that, I get magnetic field intensity at point P due to this section as 0.1544, usually considered normal. So an cap ampere per meter. Okay, now coming to section 3. So section 3 is semicircular section. Okay, CDE. So we have to find magnetic field intensity at a point P due to CDE. The conductor is the circular loop has a radius of 5 meter. Okay, that means that from point P the conductor is at a distance of 5 meter. So for such a case, yes, for a circular loop the magnetic field intensity is given by I by 2R. So here by symmetry it is half of a circular loop. Okay, so I consider magnetic field intensity half of the magnetic field intensity due to a circular loop. So it becomes half into 1 by 2R. R is 5 meter here. So I get H3 as 0.5 n cap. Now there is one more section, that is section 4. But section 4 is similar to section 2. Okay, similar to section 2. Only thing is, okay, the current is in opposite direction. But we consider the direction of magnetic field normal to the paper. Okay, I am ignoring here whether it is into the paper or out of the paper. Okay, so that doesn't matter here, because if you consider into the paper, all the magnetic field intensity will be together into the paper or out of the paper. So it is normal to the plane of the paper. That is the idea. So H2 is similar to H4. So I get H4 value also directly from the section 2 solution. So the total magnetic field intensity will be addition of all this. Okay, H1 plus H2 plus H3 plus H4. So the answer comes to 0.8281 an cap ampere per meter. So I appeal you to go for more such problems, practice it. I have taken 2 familiar problems or popular programs or common problems in exam point of view. Okay, so those are viewing my video. Okay, engineering students who apply or who appear for engineering exams in electromagnetics, these 2 problems will really help them. Okay, thank you.